Okay. So first, let me thank Professor Yao and the organizing committee for the kind invitation. So I'm happy to give a talk in this conference. There is a small mistake in the conference list because in last November I moved from Beijing University to Wuhan University. So today I give in some sense the survey talk about Landau-Ginzburg models, in particular about the quantization theory of this important model. So here is a context of my talk. Landau-Ginzburg model, or LG model, was firstly studied by physicists Gromov-Witten and many other physicists in the framework of topological field theory and the mirror symmetry in the early of 1980s. LG model appeared first as a singularity theory of polynomials. For instance, QG Saito obtained the Frobenius manifold structure on the universal deformation space of a singularity. But LG model can contain more transcendental and complicated situations. We wish to construct the quantization theory of LG models with methods from simplex geometry and geometric analysis. So let me give a definition of the LG model. So a complex LG model is a pair MF, where M is a complex manifold and F is a holomorphic function defined on M. If M is equipped with a Kähler metric G, we call it as a Kählerin LG model. Usually, we add more conditions for MG F. MG is for example, we can assume MG is a non-compact complete Kähler manifold with bounded geometry. So in application, M is usually assumed to be a Stein manifold. We also need to add some time conditions to control the 0 points of DF and its growth. For some algebraic geometers, they require that MF can be compactified to M tilde and F tilde, such that F tilde has no critical points on the boundary M infinity. So besides that, we also add some group action. Here are some timeless conditions very important in the development of the LG models. So the first one is called fundamentally tame. If there exists a compact subset K0 in M and C0 greater than 0, such that for any points outside K0, the norm of differential F should be greater than 0. The second one is called the well-tamed conditions. So if this system is fundamentally tame and also exists a compact subset K1 and a constant C1, such that for any points outside of K1, we have the following inequality. The second one is the so-called strongly tame. So if there exists a constant C such that the following relation holds, then we call this system as strongly tame. So you can see from the definition of well-tameness, it turns out there is no critical points of F outside of some compact set. So so does the strongly tameness condition. Here are some typical examples. So actually, the first type of singularities come from the study of singularity theory. So you can see the simple singularity ADE cases. And so they have the central charge less than 1. And you can also consider the simple elliptic singularities. So those are singularity with central charge equals to 1. In particular, here contains a very important example, P8, because P8 also gives a defining function of elliptic curve. we also have more singularities with central charge greater than 1. So these are the first type singularity we have studied for a long time. But with the development of research of mirror symmetry, there are more examples of LG model appearing in the literature. For example, so here I list this very simple LG model defined on this algebraic torus with a flat metrical. The potential function is defined by the by Laurent polynomial. And we can also consider a family of LG models defined on modular space M bar 1, 1 with stars function. So as follows, so we will give the details about this example. And we also have an LG model defined on the open Grassmannian. So if we consider Grassmannian manifold X, we can consider its mirror pair. So the mirror pair is given by X check. So this is a dual object of this Grassmannian in the meaning of Landau's duality. And then we take out anti-canonical divisor from X check. So we get a Calabi-Yau open Calabi-Yau manifold. And then we can take a special Laurent polynomial WQ. So this WQ is defined by pre-coordinates indexed by Young diagram. So this model is also important in the study of LG model, in the mirror symmetry of LG model. More general, flag manifold G modular P, and this LG model is given by its Landau's dual object. So this model appears in Richard's work. It's also related to Newton-Okenkopf convex bodies and appearing in the study of cluster duality. But the last two examples has never been studied from the point of view of LG model. So this is very interesting object. I have to stress here. Okay, so let us see three typical examples which are strongly tame LG models. So the first one is given by a quasi-homogeneous polynomial W. So this polynomial, of course, contains the homogeneous polynomial, and a definition is given by this equality. And so W is called a non-degenerate quasi-homogeneous polynomial. So first, W contains no monomial of the form Zi times Zj for I not equals to J. And 0 is the unique critical point of W. So with these two conditions, we can guarantee the central charge of Qi with respect to each variable is less or equal than 1/2. So this is important because from this non-degenerate quasi-homogeneous polynomial, we can get an important inequality. So which will deduce very important theory. So in my paper appeared in Archive 2011, I have showed CNW is strongly tame if W is a non-degenerate quasi-homogeneous polynomial. So the second one is given by the Laurent polynomial defined on the algebraic torus. So the metric here is a flat metrical given in this form, and the Laurent polynomial is defined in this way. It's a sum of the many monomials. So the index of monomials is given by the vertex in the lattice Cn. The Newton polyhedron delta of F is a convex Hall of the integral points of the index points. F is said to be convenient if 0 is in the interior of the Newton polyhedron. And we can consider the phase delta prime in delta. So the all-dimensional phase. And then we take the take the points of this faces as the indices of this polynomial or of this monomial, and then we can form another polynomial f delta prime. And here is the definition. So a Laurent polynomial f is called non-degenerate if for every L-dimensional phase delta prime in delta, the polynomial equations has no common solutions in T. So the first equation is given by the zero locus of f delta prime, and the rest identities are given by the derivative equations. So here is a result I obtained in 2011. So if f is a convenient and non-degenerate Laurent polynomial, then this LG system is strongly tame. So this system obviously contains the LG model mirror to Pn. So this is the second example of the strongly tame LG model. And the third one, we can consider the torus with one punctured point and G as a hyperbolic metric on T circles. And then we consider the Weierstrass function with respect to a lattice gamma in C. And then this punctured torus with this hyperbolic metric and also the Weierstrass function is strongly tame. So finally, we can show the strongly tameness will imply some existence of Hodge decomposition. I will talk this later. And then we can consider the geometrical properties of LG model. So the first one is we care about the range of this function. So we together with my students, we have proved this result. So if MF is a fundamentally tame LG model, then the range of F equals to C. And so we have the following important corollary said, let MF be a Kählerin LG model and the psi from N to M be a holomorphic embedding if the induced Kählerin LG model N together with this pullback potential function is fundamentally tame, then the range of M equals to C. In particular, the following two cases holds. Let F be a polynomial defined on the Euclidean space Cn. Then the range of F is equals to C. Of course, here is assumed to be a non-trivial polynomial. And then we can consider the Laurent polynomial F defined on this algebraic torus. We assume it has one monomial with positive degree and one monomial with negative degree. Then the range of F equals to C. So this is some result about the range of the superpotential. And then we can consider some kind of global Milnor fibration theorem. So here we let MF be a fundamentally tame LG model. Then F has finitely many critical points on M, and also the range of F equals to C. And then we can consider the real part of F. So this is an unbounded harmonic function, and we define the set for any alpha greater than 0. So this set F greater than alpha is just consists of the points such that at those points, the real part of F, the double real part of F is equal or greater than alpha. And we can also define F less or equal than minus alpha. So then now we obtain the smooth submersion from this set to this subset in C. So in general, this is not a proper mapping, and we can't apply Ehresmann's theorem directly. However, since F is a fundamentally tame, we can still get the following trivialization results. So let MF be a fundamentally tame LG model for sufficiently large alpha. There exists a diffeomorphism. So we have a fibration for this set in M. So here we can also get the diffeomorphism from this set to this fibration structure. So from this theorem, we have the isomorphism. So this relative, the middle dimensional relative homology is equals to this relative homology with respect to one fiber. And then from this result, we can get the following conclusion. So let MF be a fundamentally tame LG model. Then this quotient space and this quotient space have the homotopy type of mu n cells attached to one point. So this means this relative homology consists of mu left is simple, even we don't know the topology of the Stein manifold M. So this is the description of the geometry of this LG model. Yeah, this is interesting. Yeah, here we assume F is holomorphic. Yeah. Yes, yes. So second part is here I just propose some plan to study the deformation theory of LG model, because for the LG models you see in the definition, we have the background manifold. We also have the holomorphic potential function, and so there are different meanings to the what is called the deformation theory of LG model, and so first one, deformation as deformation of singularities. For example, people study the universal deformation of the singularity F. So this has been studied for a long time in 60s and the 70s of last century. So here is example about the deformation of AR-1 singularity. So it's given by this family of holomorphic functions, and we can also discuss the other deformation theory. Here I only need list one theorem given by Kozakov, Kontsevich, and Pantsov in 2014. So they get the so-called 10 Todorov type theorem for LG model, satisfying some very special conditions on the infinite boundary. So the theorem says there is no deformation obstruction for Calabi-Yau type LG model. Now the general question is how to describe the general deformation theory. I think this should be a very interesting problem one should explore furtherly. Okay, so you are wondering why we need to study LG model, because it appears naturally in the study of mirror symmetry. The mirror symmetry, the phenomenon of mirror symmetry is complicated and usually refer to the relation between two mirror Calabi-Yau manifolds and also probably some mirror pair of some special geometrical objects, not only manifolds. So here I give a description of very classical example about the mirror symmetry. So in the early 18th, people consider the quintical Calabi-Yau threefold. So this manifold is a hypersurface in the P1 space. It's a smooth hypersurface given by this quintical polynomial, defined by the quintical polynomial. And this hypersurface is conjectured mirror to the same hypersurface, but quotient this group action. So you get orbifold object. So physicists conjecture the the two-dimensional topological field theory of this A model should be equivalent to the topological field B theory in this part. But now we understand very good about this mirror phenomenon, because it can be explained by using the LG models. So because this can be explained as LG to LG mirror, so you can consider this polynomial defined on this Euclidean space with this group symmetry. So this one is mirror to this model. And then you can see how the mirror phenomenon appears. So here is a picture shows the relation between Calabi-Yau manifold and also Calabi-Yau type LG models. So you can see up you have this LG model. This is a model. In the other hand side you have another LG model. And below you can get the Calabi-Yau hypersurface and the mirror Calabi-Yau hypersurface. So from up to down, there is the so-called LG to CY correspondence conjecture for those objects. So here I give a very typical and a simple example how the mirror phenomenon happens. I don't want to describe the very complicated mirror phenomenon. So you see this mirror symmetry conjecture has been proved in genus 1 in mathematics rigorously by Liu-Lian-Yao and Gwinter, and genus 1 by Singer, and high genus 2 and large is now in progress, working by Chen Qihan and Guo Shuai, Ruan Yongbing. Okay, so I promise you to describe this LG model from the point of view of simplex from the simplex geometry and geometrical analysis. So here comes the A model. So the A model is you try to consider the so-called Witten equation on Riemann surface. So we can consider W, the W be a non-degenerate quasi polynomial with a form. So W is the sum of monomials written in this form. And then you can consider a Riemann surface with K marked points. So you have the low canonical bundle on sigma. So the low canonical bundle is the canonical bundle tensor some divisor bundles, and then one can define the W structure. So the W structure consists of n line bundles Li on sigma, satisfy the bound isomorphism. So you can take each monomial Wj, and then you plug in the n line bundles. Then you get a line bundle, and this line bundle is assumed to be isomorphic to this low canonical bundle. So if those n line bundles satisfy the S relations, then we say this surface with marked points and also with line bundles gives a W structure. The importance of W structure can be considered as follows, because one can consider the Witten equations using this W structure. So you see the W structure Witten equations here. So the first term is naturally defined because you have the definition of Cauchy-Riemann operator. But for the second term, you need to use the W structure to guarantee the two terms located in the same line bundle. So in this way you get globally defined equations, and then we try to construct created the modular theory from the solution space of these Witten equations. So for examples, actually this the very simple W structure has been considered for a long time as the so-called R-spin curves, because one can consider only one line bond on this surface with marked points, and then require the tensor R times of L. So this line bond is isomorphic to the log canonic bond. And then you can write down the R-spin equations. The very important thing is the so-called Witten conjecture. Says the geometrical tau function constructed by the intersection theory on the modulus space of curves satisfies the KdV hierarchy and the Villasolo constraint. So this conjecture was solved by Conservatory in 1992. And then Witten proposed later the so-called generalized Witten conjecture, because for the Witten conjecture, this corresponds to R equals to 2 cases. One can consider, arbitrary integer R, and then one should get the R-spin theory. And at this point, so Witten proposed the following conjecture. So the geometrical tau function constructed by the intersection theory on the modulus space of ADE curves satisfies ADE integral hierarchies. So related to KdV hierarchy, and also DE cases corresponds to Grunfeld-Sokolov hierarchies. So the important thing is you need to study the equations and try to consider some modulus theory analogous to Gromov-Witten theory in symplectic geometry. So after 5 to 6 year work together with Jarvis and Laurent, we get the following theorem. So given a non-degenerate quasi-homogeneous polynomial W and admissible group G, we can build a cohomological field theory, the so-called Fan-Jarvis-Laurent-Witten theory, people. So as a application of this theory, we can prove Witten's ADE singularity mirror symmetry conjecture. So this is a full genus. This is the first example for LG to LG mirror symmetry. So part of this work appeared in Annals of Mathematics and other, and also a book now reviewed in AMS publication. And we can also solve the generalized Witten conjecture for DE cases. Now we know the A1 cases. The original Witten conjecture was solved by Conservatory, and the AR cases are studied by many people, including Witten and YP Lee, and then completely solved by Faber, Shadring, and Swankinen. So we have solved the DE cases. So for DE cases, the intersection theory corresponds to the so-called Grunfeld-Sokolov hierarchy. After our work, there are many works. People try to formulate the algebraic way to construct the modulus theorem. So we have the work of Pershuk and Van Chop, and also Zhang Huailiang, Li Weiping, Li Jun, and Zhang Huailiang King and Li Jun. So further research of algebra models includes LG to LG mirror and LG to CY correspondence, gauged linear sig models. There are many important physical objects deserve further study in mathematics. So this, I think this is should be a very active direction. Okay, so this is a theory about the A model, but there is another very interesting model is the B model case, B model cases, because B model case in some sense is easy to manipulate it. So let me introduce how to describe this B model from the point of view of geometrical analysis. So this is, the knowledge of geometrical analysis. When I was a student, I learned from Professor Yau. Yeah. This including the spectral analysis, the many estimates. Okay, so you see, algebra model, Kähler algebra model is very simple, right? It consists only of the background manifolds and with a potential function. But use this simple object, we can get some complicated results. So because we can do the following things. So as usual, because M is assumed to be a Kähler manifold, so we have the Lefschetz operators L, lambda, and F. So this given by the Kähler form, and its dual operator. But the important thing is we can get the so-called twisted Cauchy-Riemann operators. We can consider d bar f equals to d bar plus df verge, and also the complex conjugates partial f. And we can also consider the sum of these two operators. Then we get a real operator df equals to the sum of d bar f plus df. This here, one should I wonder you, because this is not like the Witten deformation in the real Riemann geometry, because this operator, this twisted operator, does not keep the Hodge grading. And we use so using symmetrical, we can get the dual operators. So we have the twisted Laplacian, complex Laplacian. This is a real, and this is a complex. And we can actually we can get the following conclusions, very similar to the conclusion for compact Kähler manifolds. So here says if we put all the operators together, so all the operators forms n equals to 2 supersymmetrical algebra. So this algebra relation also, of course, including the Kähler identities. And we get the relation. So this relation shows this complex twisted Laplacian operator is just 1/2 of the real part. But I observed the unusual commutation relation. So those knowledges were known by physicists for a long time. I have no contribution to define this operator. But there's one relation didn't appear in the physical literature, is because they don't consider the Hodge star operator. If you consider commutation of Hodge star operator with this twisted Laplacian, you will find this is not a commutation relation. So this is equals to delta of minus f. So composite with star. So this identity is very important, because using this identity, we can show the first type of ring single zeta function vanishes. So this operator is very interesting because it's a matrix Schrödinger operator. You can expand it in local coordinates. Then you will find this is not the usual Laplacian defined on a compact manifold. It's a Schrödinger operator. So this brings much trouble, because in geometrical analysis, people seldom to study the properties of Schrödinger operators. So we have to create many estimates to understand this Schrödinger operator. So in particular, when acting on 0 or n forms, we have the standard form of Schrödinger operator. And we can also consider the one-dimensional algebra model. So for this one-dimensional algebra model, it has the following expression. In particular, you can consider the standard Morse function, z square over 2. And then you will find this Schrödinger operator is complex one-dimensional harmonic oscillator. So you see this model contains very important physical, fundamentally physical model. Okay, now I got the following fundamental theorem. So this theorem says, suppose that MG is a Kähler manifold with bounded geometry. If MGF is a strongly tame LG model, then that F has purely discrete spectrum, and all the eigenforms form a complete basis of the Hilbert space. This theorem was obtained by me in 2011. And then I found in literature those two mathematicians working in partial differential equation, they get the result for CNK for CNKC. Yeah. And then we can apply this theorem to study some important strongly tame system. For example, we can consider the non-degenerate quasi-homogeneous polynomial defined on Euclidean space, and also the Laurent polynomial, non-degenerate and convenient Laurent polynomial defined on this algebraic torus. So those two models are proved to be strongly tame. So we get the corresponding spectral theorem for those two models. But you see those two models appears frequently in the study of mirror symmetry. And then naturally, we have the Hot decomposition for twisted operators. So we get this one. So if we assume M to be a Stein manifold, then we can show the only non-trivial harmonic form space is a middle dimensional harmonic space, and this space is isomorphic to this Milnor ring given by F. So you see, using this method from geometric analysis, we recover the results that algebraic geometers obtained many years ago. So you can see this is the power of geometric analysis. And so besides that, the important thing is we can deform this LG model. So of course, the first situation I studied is I try to deform this silver potential, and then you can imagine one can get the variation of Hodge structure and also study the analogous Gauss-Manin connection. So actually, we can construct the TT star structure on the Hodge bundle over the deformation pyramid space. So as a byproduct, this TT star structure can recover the Frobenius manifold structure in suitable condition. And we can also study the Gauss-Manin connection. And it's related to various integral systems, for example, Riemann-Hilbert problem and the Panlev equations, and so on. So this is very interesting. The interesting thing is once you get this flat connection, you try to solve this equation. So you will find that the solutions of this the solution which are horizontal section can be described by the wave function, by the integration of wave function along the Lefschetz simple. So this is very interesting result. That means not only we can get some equations, but also can get the solutions, fundamental solutions of those systems. And you can change the LG model from one to another, and then you can get various Hodge structure and various integral systems. So I have to say this kind of study of LG model is just the start of the whole theory. So you can wonder why we need to study LG model, because I only care about manifolds, right? So I will persuade you the study of LG model is important, because we can get with my students we can get the following LG to CY correspondence. Says there is a bound isomorphism from this TT star structure coming from the LG model to the TT star structure constructed on Calabi-Yau hypersurface. So the fiber map phi tilde is given by the Baker residue map constructed by Steenbrink. So actually, the original version of this isomorphism was given by Griffiths and Carlson. Yeah, so in the name of infinitesimal Torrey theorem. But here we get more information. So what does this mean? This result says you can study, of course, if you are interested in the compact manifold, then no problem. But I can use LG model to calculate many invariants appearing in your study. Yeah. So this gives another approach to study the manifold. So because the twisted Cauchy-Riemann operator is a Schrödinger operator, it's natural to study the heat flow theory of this operator. We can study the heat kernel expansion index formula and define the torsion invariance. So this is also the joint work with my students with Fan Hao in 2020. Says if f is a strongly tamed quasi-homogeneous polynomial satisfying some conditions, the Miller number is given by the Gaussian type integral. So it can be written in this form. So interesting thing is if we take f to be this square over 2, then we obtain the Werner formula. So this is the exercise in calculus. But now you understand it has deep meaning. Yeah. It comes from the study of the heat kernel theory of LG model. And we can also define the ice zeta function. So in the usual way. But here, the different from the usual zeta function is why is called the ice zeta function? Because we take the number operates I times here. And then this zeta function is analytical in this domain, and we can prove the following theorem. So let f be a non-degenerate quasi-homogeneous polynomial, then the first zeta function vanishes. So this is very similar to what happens on compact Kähler manifolds when people study the ring single torsion. They don't study the whole sum, only half of the sum, because the whole sum vanishes, just like what happened here. And then we found that the second zeta function is important because it corresponds to the BCOV torsion invariance on Calabi-Yau hypersurface. So to define the ice torsion type invariance, we need to extend the ice zeta function. More morphically to C, this requires a symptotic formula for heat kernel. So due to a technical reason, we assume that F is a homogeneous formula. But then this condition has been abandoned by Yan Junrong and Dai Xianze. They have proved a very general claim. So then by the trace class result and the symptotic formula for heat kernel, we can define the ice torsion invariance. So here, set Fri is a regularized zeta function. So examples. So we also take the very simple example, z square over 2. So you can see this case, the second zeta function is just the Riemann zeta function. So we have the torsion here. So besides those models, because we have a lot of LG models, right? We can, for example, we can study this model, this very simple model, which is mirror to P1. And then we can prove that F is a trace operator and there is expansion. So the expansion formula is very interesting because you see in the study of Laplacian operator on compact Riemannian manifolds, only half integers appear in the index. But here we have the log term. So you can see this is a new phenomenon to study those heat kernel expansion. So this result was obtained by my student Tan Xinxin in 2018, and he also proved if we consider the deformation of f, we can get the first zeta function, but this one vanishes, and he can also get some DD bar formula for this torsion. And Yan Junrong and Dai Xianze can get more generalized result. Yes. So finally, I list some progress on the study of geometry of LG model. So we have studied the structure of differential operators, and we should also study the spectral theorem for other potential functions, right? Because for strongly tame function, this is okay, but we have many different choices. So from the point of view of analysis, it's deserved to study further those problems. And we can also consider the twisted Neumann boundary value problems. And this model has been considered by me and my student Wen Hao, now work in Nankai University. So this we can also study the correspondence between the torsion function and the BCOV type torsion. There is a conjecture there is a correspondence between the two torsions. And we can also consider LG2CY correspondence of TT star geometries between very general objects. And we also need to study the deformation theory, and we should study the relation between tropic geometry and the LG model. And finally, we also consider we have constructed some Fukaya category of LG model based on the study of Witten equations. So this result was obtained by my cooperator, my poster together in 2018. So I think I should stop here. Thank you very much for your attention.